Supervised learning. Extracting information from a topology of a data set is unsupervised learning. But when we make predictions using a topology, we often call that supervised learning. There will be some important concepts and terminology in this video. We've seen many of these ideas before, but now we're going to make them more rigorous. To begin with, a factor or feature vector is a variable x. Regular variables produce samples predictably. Random variables produce samples unpredictably. X is usually associated with a vector space, so we use a bold font. It's often a random variable, so we also use uppercase and italics. Data is a set of samples of a variable x. Typically, x is associated with Rn, so x is a column vector of the variables x1 to xn, in which case a sample is a row of length n. Later on, we'll see variables x associated with other vector spaces, such as tensors. Now, a variable x that's associated with a collection of one or more open intervals in R is called a continuous real variable. That is, if little x equals p is an instance of the variable capital X, then for some delta greater than 0, every number in p minus delta, p plus delta open interval is also a possible instance of x. In other words, there's a continuum of possible values of x. A continuous random variable is a continuous variable whose samples are unpredictable, have no pattern. A discrete variable is associated with a set that contains no open intervals, such as a finite subset of R. A function has only one output for each admissible input. Those admissible inputs are known as the domain of the function. The input variable x is associated with a vector space. The output is typically R real variables y1 to yr. And there are also going to be parameters, which we'll indicate, at least initially, using beta. So our models are of this form. We have a tuple of y1 to yr is equal to some function of x given these parameters also in the model. If x is associated with Rn, then our models look like this. The y1 to yr is a function of x1 to xn, and there also are parameters. For now, we're just going to use Rn, but we can use these ideas for x associated with any vector space. A function has only one output for each input and some parameters. So the function is actually a family of functions parameterized by its parameters. Training means finding the values of the betas that correspond to the best model for the data. For example, the logistic model. Here, our variable x is the column vector x1 to xn that's associated with Rn. So we have a model of this form. But we also only have one output variable, so actually we have a model of this form. Suppose we define a vector beta of the parameters beta 1 to beta n. Then beta 1 x1 plus dot 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 up to beta n xn is actually the vector beta dot product the vector variable x. And that means we actually end up with this form of the logistic model. X can be associated with any vector space that has an inner product, and we'll use this idea later. So supervised learning is really about functions. In an earlier video, where big data is difficult to classify, we introduced regression and classification based on the idea of labeled data. So when we have labeled data, we have instances of the x's Those are instances of the features, and instances of the y, those are instances of the responses. Or another word for that is samples. Samples of the features and samples of the responses. Features, we'll assume, are continuous random variables. And the prediction problem is to estimate values of the parameters for which the model best predicts a response given a sample of the features. In other words, supervised learning is the study of these types of models and their relationship to this type of structured data. For example, linear regression. So given points in the plane, we split into a training set and a test set. We build a model using our training set. We test the model using our test set. But for now, let's just focus on building the model. So our model is f of x with parameters mb, which is just mx plus b. We tend to look at what's called the total squared error, or mean squared error. Remember, p is the number of observations or samples in the training set. Why c? Well, we'll explain that later. The best parameters are those that minimize c of m comma b. We can take partial derivatives, the partial of c with respect to parameter b, the partial of c with respect to parameter m. And now we can do something that is only possible in the most elementary and impractical models, at least in this class. We can find the solution to the equations, the partial of c with respect to b equals 0, the partial of c with respect to m equals 0. And here they are. But for big data, this approach is neither desirable or practical. So here's some key observations. M tends to be huge. That's the number of samples. Big data is messy. For example, the 3 sigma rule says that an outlier only has a 0.27% chance of occurring. But that still means about 3 outliers per 1,000 observations. And a single outlier can really change the least squares the line of best fit. But we trust, high veracity is important, that the samples are collected independently. Now, what do I mean by independence? Well, let's suppose you draw a card from a deck of 52 and then you draw another card. Independent samples would mean the first card drawn is returned to the deck, so the second draw is also from a deck of 52 cards. Or you might have the second card drawn from a different but identical deck of 52 cards. That's an independent experiment. Now we can play a game after we define concepts of uncertainty and loss. So given data and a model, a loss function is a measure of uncertainty in using the model to approximate a true label. Now we're using loss in the sense of this following exchange, for example. Can you answer my question? No, I am at a loss as to how to respond. So this is what we mean by loss, how much we deviate from perfect knowledge. Perfect knowledge is certainty. Certainty is that the y hat sub I is always equal to y sub I. In other words, the loss would be 0. A batch is a much smaller subset of the data. The law of large numbers says that if samples are independent, then the limit of expected loss over batches converges to the true expected loss of a model over that data. An idea we'll explore in one of the associated notebooks. Our goal is parameter values that minimize expected loss. This motivates an entirely new conceptualization of functions as layers. So we have functions of this form, a response, and a model and parameters, also known as a transformation or mapping. But modern interpretation is as a layer. Parameters are internal or local to the function. Supervised learning means that the parameters are estimated using data of this form, labeled data. So independent variables are inputs to the layer, and dependent variables are the outputs from the layer. The forward direction activates the function on instances of the variables. The parameters are fixed during activation. So we have these instances that move through and give us these y's. This is called feed forward or activation. The backward direction uses a loss function to train parameters given instances of the variables. So we have fixed instances of the variables, and then using derivatives with respect to the parameters, we get new values of the parameters, which is called backpropagation or gradient descent. So let's look again at linear regression. Now as a layer where the m and the b are parameters. We have a loss function, which is y hat minus y squared. This is the mean squared error loss. The expected loss, or the cost, is c of mb, which is 1 over p, I equals 1 to p of the loss functions at the data points, which is now our total squared error function. So we have an instance or a sample, and it feeds forward to give us, for the current m and b parameters, an activation. Then we minimize the loss over batches of these activations. And that gives us new values of the parameters. So let's look at a very important special case known as sum and fire layers. Here we find internal variables z1 to zr, which are sums of products of the parameters times the input variables. They're actually inner products. We then define an activation function y equals sigma of z, and we apply that to each of these internal variables, along with an intercept or bias. These activation functions have to be continuous, non-decreasing, and bounded below. Something like that. So let's see what this would look like for a single response. That would look like that. One single z variable. Y is sigma of the z plus the beta I, the bias. So remember our simulated calculus grades. We're going to look at classification, particularly using the previous and first 4 exams to predict whether or not a student passes the class. So our goal is a model which predicts pass from previous and the first 4 exams. And this is what our data looks like. These are our features and our response, and so therefore this is what our model looks like. We can define f in this form, x0, x1, x2, x3, x4, and then all those parameters is the activation sigma on all of that linear combination of variables. But we can do something very clever. What we can do is we can introduce parameters as weights on the edges, in which case this sum is just this long linear combination. And then we apply the activation function. Now what if we add a constant input of 1 with the intercept parameter beta sub I? Well, what we have in that case is now the beta sub I corresponding to a constant 1 plays the same role as all the rest of them. So when we define our internal variable, it truly is just the sum over k beta sub k x of k, where the x sub k when we get beta sub I is just the number 1. Now we have our z internal variable and our activation function. And we need a suitable activation function of one variable. So having done that, this is what our model looks like. Much more compact form. And this is the sum and fire model for our data. There are many choices for an activation function, sigma of z, but let's just choose a now familiar one, the logistic model. So when the sum is less than 0, the probability of being class 1 is less than 50%. When it's greater than 0, the probability of being class 1 is greater than 50%. So we've transformed to linear separation. And we've incorporated the logistic model into our modern understanding of function as a layer. So if we did this with logistic regression, then we would read in our training data, and then we'd use the scikit-learn methodology, create the learning object, fit the object to data, analyze the results, which after fitting are stored in the object itself. So here we do that. We train with data, but we test with a different data set, data prime. So we read in some test data, and then we drop exam 5 and let y-test be just whether or not they passed or failed. And then we score the classifier on the test data. And notice that it scores a 93% accuracy. So logistic regression implies linear separation. Suppose we only look at exams 3 and 4. Then this is what the data looks like. Their decision surface is the probability or confidence of class 1 at each point in the feature space, which in this case is the xy plane. We're only using 2 features. And we end up with this kind of a decision surface. And where we have the blue is class 0, and where we have the red is class 1, and then it changes to a yellow and a bright color. That defines the margin. So it's not linearly separable, but logistic regression assumes linear separation. It's almost linearly separable, though, at least visually. In other words, we could put a margin in, and then that margin could give us very high accuracy as long as we weren't looking at points in the margin. Or we could come up with what's called an absolute margin, which means there are no mislabels outside of that margin. So logistic regression is an equation model. It has low model complexity, and it has high bias, often implies a large margin. And that's why we see this margin being so large as it is. With supervised learning, we use labeled data to estimate parameters. F is often an algorithm model, the function f defined by an algorithm, although it may begin as an equation model, such as logistic regression. An equation model, very often we end up having to use an algorithm at least as a numerical method for estimating the parameters. The backwards is almost always an algorithm. And then we used our trained model to predict test data responses.